Hello and a warm welcome to everyone. It is my honor to present at this year's SEEDS conference. This research was conducted in fulfillment of the degree Master of Science in Construction Management, completed through the Department of Construction Management at Nelson Mandela University. My name is Ashvin Manga. I was the principal investigator under the supervision of Christopher Allen. Before presenting the research, I will introduce and provide a brief history of computer vision. Human vision is amazingly beautiful and complex. The journey to the vision we experience today started billions of years ago when tiny organisms developed a mutation that made them sensitive to light. That single mutation developed into the visual system we see in most animals on Earth today. The basics of the visual system are eyes for capturing light, receptors in the brain for accessing it, and a visual cortex for processing it. Computer vision or machine vision is the technology that extends the visual ability of human vision to machines, and we have made some exciting progress. The first type of photographic camera was invented around 1816, and at its core the technology used silver chloride that darkened when exposed to light. 175 years later, in the late 1990s, we had consumer digital cameras. Essentially, the technology that mimics the eye and the visual receptors was mastered. However, this was the easy part, and creating the technology to perform the function of our visual cortex was the challenge. Not surprisingly, the technology that allows computers to understand the context of images and videos is based on our own biological neural networks, and as such are called artificial neural networks. Computer vision began as a stepping stone into artificial intelligence around 1960, with the first systems being able to differentiate letters of the alphabet. A mere 61 years later, and the challenge of the self-driving car is being solved by Tesla using computer vision as the core technology of their full self-driving system. The aim of this research was to improve facility management by counting occupants in real time using existing lecture venue CCTV cameras and computer vision analysis. Occupant count was compared with carbon dioxide and particulate matter levels to assess HVAC performance. To complete the study, a quantitative case study methodology was used. Lecture venues at Nelson Mandela University's North and South campuses were used as a case study to collect numerical data on the number of occupants during lectures by leveraging existing CCTV cameras and a custom computer vision application to count occupants in real time. Indoor air quality was measured using the Air Visual Node Pro. The computer vision application was created in the Python programming language and utilized YOLO v4 and DarkNet to train the detection model weights. The dataset in which the computer vision model was trained on was created from Google Open Images dataset version 5. The training dataset was 5,000 images and the validation dataset was 2,500 images. The computer vision model was trained using Google Colab, utilizing the superior GPU facilities. The model was trained in DarkNet and used the pre-trained convolutional layers of the YOLO v4 network available on GitHub from Alexi AB. The model was trained to 30,000 iterations over a period of 28 hours. The model was validated using a separate validation dataset and was deemed fit for use at a mean average precision of 72% and an average loss of 1.2. The real-time occupant detection results from 8 different lecture venues vary greatly, with occupant detection accuracy of 96% and 13%. The main reasons identified were changes in light levels within the venue, the quality of the existing CCTV camera, and the position and angle of the CCTV camera within the venue. The power of computer vision applications are unlocked with the creation of large label datasets that can be used to train computer vision models. Further research is required in this area if we are to leverage computer vision in the manner in which Tesla is utilizing computer vision. Perhaps more importantly is further research into innovative methods of easily creating large training datasets for built environment applications. There are numerous undiscovered computer vision applications within the built environment, from fall detection in elder care facilities to leak detection within water infrastructure. The results obtained from this research provide evidence for the use case of computer vision for occupancy detection within the built environment. This concurs with a number of authors that have conducted similar research. I would like to conclude by highlighting that all the resources used to create the computer vision model applied in this research were free and online resources. To me, this is extraordinary. Every single business in the next decade will have to implement artificial intelligence to process data and provide business insights or consumer services. This will be driven by the massive return on investment for implementing AI and competition from businesses that leverage AI. A great example of this is the full self-driving technology developed by Tesla. Full self-driving, or FSD, will allow a fleet of autonomous taxis that will compete extensively with Uber and potentially disrupt the ride-sharing industry to such an extent that Uber and similar businesses will be made redundant. Facility management firms that wish to leverage artificial intelligence need to begin collecting and creating labeled visual datasets that can be used to train computer vision models. The beauty of computer vision is that it is software, meaning you can continuously improve your product or service with updates. This is the main reason Tesla uses computer vision and not LiDAR, because cameras are cheap and high quality, and computer vision is software that allows significant improvements to an entire fleet of vehicles with no hardware changes. Thank you.